In the last lesson, we turned R, L, and C into impedances. Once that replacement is done, the network laws do not change shape. Kirchhoff's voltage law is still a loop sum, and Kirchhoff's current law is still a node balance. The only real difference is that the coefficients are now complex. Start with ACKVL. In a series RL loop, the source phasor equals the sum of the element drops. So V sub S equals IR plus I j omega L, or I times the quantity R plus j omega L. Same loop rule, same topology, new impedance labels. Now ACKCL. At a node fed by a current source, incoming current equals outgoing branch currents. If one branch is a resistor and the other is a capacitor, then I sub S equals V over R plus V over Z sub C. Since Z sub C equals 1 over J omega C, this becomes I sub S equals V over R plus J omega C times V. Same node logic, new complex coefficients. This is why node analysis still works. If the node voltage V is the unknown, collect the admittances connected to that node. For this example, V equals I sub S over the quantity 1 over R plus J omega C. The workflow is still isolate the unknown and solve. The only change is that the coefficient is complex instead of purely real. Mesh analysis also survives intact. Define mesh currents I1 and I2 exactly as before, then write A, C, K, V, L around each loop using impedances. The shared resistor couples the two equations, so the result becomes a small complex linear system. You solve it the same way you would in DC, just with complex arithmetic. In practice, the recipe is short. First, replace R, L, and C with impedances. Second, write KVL, KCL, node or mesh equations with phasors. Third, solve the complex equations for the unknown phasors. After that, convert back to magnitude and phase, or to the time domain only if the problem asks for it. So AC node and mesh analysis are not new laws. They are the same Kirchhoff laws in the impedance domain. In the next lesson, we will use this viewpoint for AC source transforms, Thevenin equivalence, and Norton equivalence.